Okay, in this problem, we're trying to figure out how to make this di-substituted cyclopropane from propene. So let's start by working backwards. And the method we have to make cyclopropane is through something like the Simmons-Smith reaction. So just working backwards, a cyclopropanation of this trans alkene will give us that cyclopropane. From there, if we want to think about the carbons that we have, let's just say these three carbons come from these three carbons. Well, the best way to add carbons from the methods we've discussed is through alkylation of a terminal alkyne. So this alkene could have come from an alkyne with a methyl and ethyl group. This di-substituted alkyne could have come from this terminal alkyne plus whatever halogen, a haloethane. And then this alkyne, the way we could get that from the alkene would be through halogenation and elimination. So we can get that from our starting alkene. So let's work this in the forward direction so that we can see all of these steps. Let's start with our alkene. Okay, in order to convert this to the alkyne, we need to do the two-step halogenation and elimination. So let's halogenate this first. We'll just add bromine. And that gives us the dibromoalkane. You'll remember this reaction from lab. We do two eliminations of HBr. You can use whatever base you want. We'll just use hydroxide, heat it up to help things along. That will eliminate the dibromide to give the alkyne. From there, we can treat this with a base to form the acetylide ion. In class, we used NaNH2 as the base, where NH2 minus is our base. You could use something like butyl lithium, where we have lithium plus and butyl minus as the base. What that's doing, it's taking the proton off the terminal alkyne, to give us the acetylide ion. From there, now we can add our alkyl halide to alkylate that position to make this an internal alkyne. Let's just use ethyl bromide. So that will act as a nucleophile, attack the carbon that has the bromine directly attached. And we're going to add these two carbons to the end of the alkyne. Carbon 1, carbon 2. Okay. From there, so now we have this di-substituted alkyne, we need the trans alkene. So we need to do a reduction. Our choices to do an alkyne reduction to an alkene we have the dissolving metal reduction, which will give a transalkene, or hydrogenation with Lindlar's catalyst, which will give us the cisalkene. We want the transalkene, so let's use the dissolving metal reduction. We'll use sodium metal, liquid ammonia, and low temperature. That will give us this transalkene. From there, we can do the Simmons-Smith cyclopropanation. We'll do CH2, I2 diiodomethane, and this zinc copper couple. That forms the carbene, which adds this carbon across the double bond. So we get the cyclopropane, and now our ethyl and methyl groups will be trans. So here's our ethyl. We'll do that one out, and the methyl back. We also will get the enantiomer in this step. Okay, if you need a little bit of review as to how this elimination step here occurs, we'll go ahead and take a look at that on the next page. Then we're going to react this with a base. Let's just stick with hydroxide. This might be written as NaOH or KOH, regardless you have your hydroxide. So what we're going to do here is we're going to eliminate H and Br across the carbon-carbon bond. So what I can do is I'm going to go ahead and draw in a hydrogen on this carbon and a hydrogen on this carbon. Okay, so first, it doesn't matter which one you do first. Let's go ahead and eliminate across the bond this hydrogen and this bromine. The way we're going to show the electron movement for that, our base will come over, grab the proton. These electrons will collapse down to give us the double bond, and we'll lose Br minus. So we get that. Also, our byproduct here would be water. Okay, now I'm going to go ahead and show this other hydrogen. Okay, this step's not quite as easy, which is why we typically heat this up. But now our base can come in and go after this hydrogen, which will eliminate this H and the neighboring Br. So we'll push those electrons down to form the triple bond and lose the other Br minus. So we get our alkyne, Br minus, and water.